Hello, students! Have you ever thought about this? How do chemists mix some very reactive ingredients for a reaction without the liquid itself, the solvent, interfering? Well, today we are going to explore the solution to that very puzzle. And the answer is a fascinating functional group called ethers. So, let's begin.
Okay, so let's start with the central mystery here. It's a puzzle that every single organic chemistry student will face in the lab.
Just think about it. You are in the lab trying to prepare a very sensitive, very reactive chemical. Now, you need a liquid, a solvent, to dissolve everything, right? But the problem is, most common solvents, like water or even alcohol, are themselves reactive. They will just jump into your reaction and spoil the entire experiment. So, what is the solution?
And this is exactly where ethers come to the rescue. You can think of them as being the perfect non-interfering medium. They solve this big problem because they are surprisingly, wonderfully unreactive.
So, what exactly is an ether? Well, at the most basic level, it's an organic compound where one oxygen atom is bonded to two carbon atoms. It forms this kind of a bridge, a COC bridge. And this is the fundamental structure that you must remember.
And this COO structure, this is the secret to their entire personality. It's what makes them polar enough to dissolve many different compounds, but at the same time, it makes them incredibly stable, almost shy when it comes to reacting.
So, the big question is, why? Why is this structure so stable? To understand this, let's build a very simple mental picture. We're going to use an analogy that will make this concept crystal clear for you. I want you to imagine the oxygen atom in an ether as a very shy person at a party. You know the type. They don't want to talk to anyone new. They don't want to interact. So what does this person do? They find their two best, most protective friends, and they stand right in between them for safety.
So, let's map this analogy properly. The shy person, that is our oxygen atom. The two protective friends on either side, those are the two carbon atoms. And what is the result? The oxygen is completely shielded. It is protected. It becomes unavailable for any new interactions, and that's what makes it so stable and unreactive.
Okay, now let's actually build this mental picture in our minds, step by step. First, imagine the two carbon atoms. These are our protective friends.
Next, we take our shy oxygen atom and place it right in the middle, sandwiched between these two carbons. See? This is what forms that characteristic COC bridge. The oxygen is now, it's locked in place. And now, for the most crucial part. The oxygen's lone pairs of electrons, the very things that are usually responsible for reactions, they are tucked inwards. They are shielded by those bulky carbon groups, so you can say they are sterically hindered. They are hidden away from the outside world, making them totally inaccessible for any potential reaction.
Okay, now let's compare this to their chemical cousins, the alcohols. It makes the difference very clear. Look at the table. In an alcohol, the oxygen is at the end of the molecule, it's terminal. It's like an outgoing person, with its reactive OH group totally exposed to the world. But in an ether, see? The oxygen is internal. It's like our shy person, safely protected inside that COC bridge. And this structural difference is why alcohols are reactive and can form hydrogen bonds, while ethers are inert and cannot.
All right, so we've established that ethers are shy and unreactive. But so what? How is this property actually useful in the real world of chemistry? Why should we care about this?
Well, this inertness is exactly what makes them such superb solvents. They solve what we can call the Goldilocks problem in chemistry. You see, they aren't too reactive, like alcohols, but they also aren't too nonpolar, like simple hydrocarbons. They are just right. That CO bond gives them just enough polarity to dissolve many compounds, but their overall shielded structure makes them unreactive, so they don't interfere.
And in fact, this special property makes them the absolute #1 choice for one of the most important reactions in all of organic chemistry, the Grignard reaction.
You see, Grignard reagents are extremely reactive. If you try to put them in a solvent like alcohol, that reactive OH group from the alcohol will immediately attack and destroy your Grignard reagent. The reaction would just fail completely. But if you use an ether solvent, like tetrahydrofuran, which is commonly called THF, it provides a safe, inert environment. The ether dissolves the reagent, but then it leaves it alone to do its actual job. It's the perfect partner.
This simple chart shows you the difference perfectly. Look at the first bar. If you take an oxidizing agent and add it to an alcohol, it reacts very quickly. You'll see things happening. But now look at the second bar, for ethers. Under the very same conditions, there is almost no reaction. This really visualizes that dramatic difference in their chemical personality.
So, to finish up, let's do a quick recap. What are the 3 key points you must take away about ethers? First, the core idea. Ethers have a protected oxygen atom sandwiched in that COC bridge. Second, the mental image. Just remember the shy person analogy, where the oxygen is shielded by its 2 carbon friends. And third, the application. This inertness makes them the perfect, non-reactive solvents for very important reactions, like the Gridyard reaction.
Honestly, if you can just remember these 3 things, the core idea, that mental picture, and 1 key application, I promise you this topic will feel much, much lighter for your exams. Now, I'll leave you with one final thought. Based on this very unreactive nature that we discussed, can you think why that same property might make ethers good anesthetics? Think about it. I hope this explainer was helpful for you.